yesterday we were going over acceleration. Basically all we got done was defining what acceleration is. Okay, it's a change in velocity over time, that it can be represented by the slope of a velocity versus time graph if it's a linear relationship. Okay, and we reviewed the formula that we used to calculate acceleration from last year. Okay, that would be that acceleration is the change in velocity divided by the change in time, or Vf minus Vi over t. Okay, that's the one you used last year. And we went over as well how this is the slope formula for a linear velocity versus time graph. Okay, and that m equals y minus b over x. Okay, where on a graph of meters per second and seconds, okay, that's linear, b would represent Vi. Okay, the y value for this particular point here would represent Vf, and obviously the x value would represent the elapsed time from 0 to x. Okay, so this just translates into this formula. Right, that's what we went over yesterday. Okay, then we did one problem where we had to use Vf minus Vi over t and solve. I think we solved for t yesterday on the problem that we did. Okay, we just finished that at the end of class. So what I want you guys to do is try these two problems. They use that same formula. Okay, see how you do on those, and then we'll go through them together, and we're going to move on to the other formulas today. We're going to look at how each one of those formulas works, how you manipulate them, and so on. Okay, so that's what we'll be doing. Okay, let's have to work on those two. Okay, let's have a look at number one, because I'm sensing that number two is giving people trouble because of the units.
Yes.
Okay, so we'll have a look at that in a minute, but let's go over number one first. Okay, so we have a motorcycle with an initial velocity of 6 meters per second. All right, so first step here is write down my given, 6 meters per second. It accelerates at 4 meters per second squared. Sorry, I should also write that that's east. Okay, the acceleration is 4.0 meters per second squared east. Right? We're looking for how long it will take, that's time, for it to reach a final velocity, okay, of 36 meters per second east. All right, so all the stuff is in the same direction. It's all east. Right? So you don't have to worry about vectors here making anything positive or negative. But we need to solve for time. So I have A equals Vf minus Vi over t. Okay? If I want to solve for t, what do I have to do with it? Okay, how do I manipulate it? Right, multiply both sides by t. Right, if I want to move something, I do the opposite. Okay, and in this case, I want to move t because I can't solve for it if it's on the bottom of an equation. I need to move it to the top. So I'm going to multiply both sides by t. Then I will divide both sides by a, and that'll be my manipulated formula solving for t. Okay, so when I do that, I'll have 36 meters per second minus 6 meters per second divided by 4 meters per second squared. Okay, so 36 minus 6 is 30. Okay, and then we're going to divide that by 4. It's really like 7 point something. So 30 divided by 4, and give me 7.5. Okay, but what's the problem? Sorry, 7.5 seconds. I'm done with that. So time is 7.5 seconds. All right, everybody okay with that? Yeah. Now, for question number 2, okay, the point of question number 2 is to illustrate to you that whenever you perform a calculation, your units for the same measurements need to match. Okay, so in question number 2, they're telling me the velocities in kilometers per hour. All right, so in that velocity, the units for time are hours. But then they tell me that it accelerates at 1.5 meters per second squared, and then gives me a time in seconds. I can't divide those numbers. I can't put them in an equation together because they're not the same. Okay, it's like dividing apples by oranges. I don't know what that gives you. Okay, it doesn't give you anything real. You have to have them in the same units. So you have to convert the kilometers per hour into meters per second, and you do that by performing a compound conversion. You may or may not have done one of these before. Okay? So in this case, it tells me I have 20 kilometers per hour. I need to convert that to meters per second, which means I need to convert the kilometers to meters and the hours to seconds. All right, so I'm going to have two conversion factors that I'll multiply by. All right, so the first thing I want to do is convert the kilometers to meters. There are 1,000 meters in 1 kilometer. Okay, so multiplying this number by 1,000 will convert it to meters. My kilometers will cancel. Everybody all right with that? Okay. In 1 hour, there are how many seconds?
60 minutes.
There's 60 minutes, and in every minute there are 60 seconds. 60 times 60 is 3,600 seconds. Okay? So, in 1 hour, there are 3,600 seconds. So now my hours will cancel. So effectively, what I'm doing is I'm taking the 20, I'm multiplying it by 1,000, and then I'm dividing it by 3,600. Okay? Now, I can shorten this a little bit. Okay? If I divide 1,000 by 3,600, okay, effectively, it's the same as doing this. Instead of multiplying by 1,000, then dividing by 3,600, I might as well just do this. Okay? Multiplying by 1,000, then dividing by 3,600 is effectively the same as taking one step where I divide by 3.6. Okay? So, if I want to convert from kilometers per hour to meters per second, I divide by 3.6. If I want to go the other way, I would multiply by 3.6. 3.6 is the magic number. Okay? To convert kilometers per hour into meters per second.
We have to memorize how many seconds are in an hour.
Yeah, you should. That's not something you should memorize. It's something you should be able to figure out. Right? There's 60 seconds in a minute, and there's 60 minutes in an hour. Multiply.
What about like kilometers and
Yeah,
meters?
you live in Canada where we use the metric system. You should know that there are 1,000 meters in a kilometer, that there are 100 centimeters in a meter, there are 1,000 millimeters in a meter. Yes, you should know that. Yes, you should memorize
But
that.
how many feet are in it?
Well, we don't do imperial, so you don't need to worry about that. Well, you'll never get something in feet. Okay? You'll never get a question that has miles, feet, inches, anything. Okay?
Centimeters and millimeters?
Millimeters, all metric. Okay?
Micrometers?
Yes, maybe micrometers. Okay? So yes, at this point we do expect that you know that. That's the beauty of the metric system though. Meters, grams, doesn't matter. All the prefixes are the same. There are 100 centimeters in a meter. There are 100 centigrams in a gram. Okay? It's all the same. There's 1,000 grams in a kilogram. There's 1,000 meters in a kilometer. Kilo means 1,000. Okay? That's the beauty of the metric system. You don't have to remember that there are 12 inches in a foot, 3 feet in a yard, 5,280 feet in a mile. You don't have to remember all that crap. I do, but you don't have to. Okay? You just have to remember everything's 10 times bigger than the level before. Okay? Way, way easier. It's why everyone except our neighbors to the south have switched. I don't know what. Okay, recording. People from the States might hear this. His name is, he lives at, okay. I wouldn't do that to you, Sheldon. I protected your identity. Okay. So, everyone follow on that. So now, if we're looking at this one here, okay, obviously it's an acceleration question. So the first thing I want to do is convert the initial velocity here into meters per second. Okay, so I'm going to divide the 20 by 3.6 to get it in meters per second. Okay, 5.55 seconds. Or sorry, meters per second. Sorry, 5.5 repeating meters per second. Okay, it accelerates at 1.5 meters per second squared. And that's north, so is this. Right, and it does that for 9.3 seconds. And we're looking for its maximum velocity in kilometers per hour. But we'll calculate it in meters per second and then we'll convert. Okay, so we got a new manipulation here of this formula. A equals VF minus VI over T. All right, so quick reminders of the rules of algebra. Rule number 1, if I want to move something, do the opposite. What I do to one side of the equation, I do to the other, okay? And the other rule of algebra is move what's not attached to what you're looking for first. Okay? I'm looking for VF. What part of this side of the equation is not attached to VF? T. All right, so I'm going to move T first. I'm going to multiply both sides by T. Then I'm going to add VI to both sides. All right, so here's what I want you to kind of realize about this equation right now. VF minus VI is the change in velocity. That equals T times A. All right? If I move VI over here, I'm saying take the initial velocity, multiply by, and add it to the change in velocity, and that will give you the final velocity. That should make sense logically. I started with this much, I changed by this much. When I add them together, I get my final velocity. Everybody all right with that?
Yeah.
Okay. So when we plug in our numbers, we're going to have our 5.5 repeating, okay, plus 9.3 times 1.5. And that'll give us our final velocity in meters per second, and then we'll convert it. So plus 9.3 times 1.5. All right, so I'm getting 19.5 meters per second. I'm going to multiply that by 3.6 to get it back into kilometers per hour. All right, 70 kilometers per hour. And that's north. Okay, is that ringing a bell from last year? Hopefully we're able to manipulate that equation.
You still we're gonna have different acceleration.
5. I did say a big number, but I wasn't.
You don't need to memorize them.
You don't need to memorize them, they're on your phone. Okay? All right, everybody ready? Okay, so I want you to copy this one down. Okay, this will be our first example of the next acceleration formula that we're going to be using. Okay, so I have a cattle train traveling west at 16 meters per second, and it's brought to rest in 8 seconds. Find the displacement of the cattle train while it is coming to a stop. Assume uniform acceleration. Okay, that's important. Okay, if it's not uniform, there's one formula we can't use. Okay, we need to know that this is uniform acceleration. Okay, first step, we got to write down our givens so we can figure out which of the 5 acceleration formulas we have is going to be applicable to this question. All right, so we're traveling west at 16 meters per second. That's VI. Okay, and that's west. Okay, it's brought to rest. What's VF? 0. Okay, in a time of 8 seconds. It wants to know the displacement of the cattle train in coming to a stop. All right, so this formula that we're going to use doesn't have acceleration in it. We only have one formula from our list that's an acceleration formula that actually doesn't have acceleration in it, and it's this one. D equals VF plus VI over 2 times T. Okay? And again, that's the importance of writing down our givens. Okay? We write down our givens so that we can figure out which formula to use. I can't use any of the formulas that have acceleration in them because they don't have acceleration. And, I mean, sure, I could calculate acceleration using another formula and then use another formula to calculate displacement. But why would I do a question in 2 steps that I could do in 1? Okay? The answer is you wouldn't. But if you didn't figure that out and you did it in 2 steps, you could still get the right answer. It would just take you longer. Okay? And on an exam, you don't want to take longer doing stuff. Please.
How do you know what was the initial and final velocity?
Well, because it said it was traveling west this fast and was brought to rest, which means this was how it started.
What if you start here?
No, it tells me it was traveling at this speed. Right? A cattle train traveling west at this speed is brought to rest. So this happened first, and this happened second, according to the story. Okay? It is brought to rest from this sweep. Okay? It's just reading comp. We have to read the question and go, okay, this was the initial, this was the okay? I can't bring something to rest if it wasn't already moving. That's how I know rest is the final velocity. I can't bring it to rest if it wasn't already going somewhere. Does that make more sense?
Yeah, I thought it started at 0.
No, brought to rest. Starts from rest, that's VI is 0. Brought to rest, VF is 0. Okay? All right, so we need to solve this for D, which means, great, I don't have to manipulate this equation, right? It's already solving for D. All I have to do is plug in the numbers that I have. So that'll be 0 plus 16 divided by 2 multiplied by 8 seconds. So 16 over 2 is 8 times 8, 64 meters west. Okay, how do I manipulate this equation? Okay, so if I have this equation to start with, D equals VF plus VI over 2 times T, and I want to solve for T. What do I do? Done?
You multiply by 2, and then you would subtract.
Is that whole thing in brackets?
Yeah.
Okay, can I move it all at once?
Yes.
Yes, I can. Okay, think order of operations. Order of operations says this is a number in brackets. I need to know this number before I do anything else in the equation, which means it's like saying D equals X times T. If I want to get T by itself, I just do what with X? Divide. Okay, I can divide this whole thing over because it's all in brackets. Okay, that's one of those kind of tricks of algebra. So to manipulate for T, it'll be D over VF plus VI over 2. And if you recall, yesterday we said this is really just calculating the average velocity. So if we're looking at V equals D over T, okay, when we calculate T, right, it's D divided by V, which is what we have here. D divided by average velocity equals time. Right? Same kind of formula there. All right, what if I wanted to calculate VF? Okay, how do I get rid of the brackets? What should I move?
Divide by bracket.
Move T. Okay, the only reason that I have brackets there is because T is on that side, and I need to do this operation before multiplying by T. So if I divide both sides by T, I don't need those brackets anymore. There's nothing else on that side. So the brackets effectively disappear after moving T. So now, how do I get VF by itself? Multiply by 2. All right, so 2 is going to come over there. And then subtract VI. So I'll have 2D divided by T minus VI. And it would be the opposite if I was looking for VI. It would be 2D over T minus VF. Okay? Everybody with me on that? Okay. Try these two. They use that formula. Give you a few minutes and then we'll walk through them. So for number 1, we have like a hound, like one of those racing hounds, okay, running at a velocity of 16 meters per second south. So there's our VI. 16 meters per second south. Okay? It slows down uniformly. Again, that formula that we're using only works for uniform motion to a velocity of 4 meters per second south. Okay? And it does that in 4 seconds. All right, find the displacement of the hound during that time. Okay, so again, I don't need to manipulate the formula for this question. It's already set up to find the displacement. So all I have to do is plug in my numbers. Okay, so D will equal 4 plus 16 divided by 2 times 4 seconds. So 4 plus 16 is 20, divided by 2 is 10, times 4, 40 meters south. Okay, would be my displacement, or the hound's displacement during that time. Okay? How many people are struggling with number 2? Okay. So the thing you need to notice about number 2 is that one of the numbers given to you is up the hill. The other one is down the hill. How are up and down related? One's positive, one's negative. You need to reflect that in your math in the equation. You need to make one of them positive and one of them negative when you're solving for that one. So I'll give you a couple more minutes to try that one with that and see how you do. Okay, so for number 2, I have a ball that's moving up a hill, okay, with an initial velocity of 3 meters per second. So VI is 3.0 meters per second up, okay, uphill, to be more specific. Okay, 4 seconds later, okay, and this is an important point to make here. They wrote 4 seconds as a word. How do I treat that in terms of significant digits?
4 ones.
No, infinite. It's a counted number. I have no idea how accurately it was measured. Therefore, I have to treat it as though it is infinitely accurate because I don't know. Okay? I can't say it's 1 because I don't know that either. Okay? I have to rely on all the other measurements, which is why you will never again see that done. Typo input. Okay? It should never have been written that way. You cannot write a number as a word, okay, unless it is a counted number. And nobody counts seconds. Okay? You can't, that's not measuring, it's counting. It's not the same. Okay? So, I'm just going to say it's 4.0, but I'm not going to let it affect my significant figures. Okay? It's moving down the hill at 9 meters per second. We are looking for the displacement of the ball, so once again, we don't have to manipulate, but okay, we're solving for D. Okay, the important part here is that I'm making down the hill negative and up the hill positive. Oh, sorry, divided by 2 times 4. All right, so negative 9 plus 3 is negative 6. Okay, negative 6 divided by 2 is negative 3. Negative 3 times 4 is negative 12 meters. But can I leave it like that? No, the question gave me up the hill and down the hill, so it'll be 12 meters down the hill. Okay, they are wrong. Okay, you cannot give up and downhill as a direction and then leave an answer as negative. Okay, that's not the same directions you were given in a question. So keep that in mind when you're given your vector additions. Because if you're given east and west in a question, you wouldn't want to answer it as negative. Okay, east or west. All right. Write this one down, and then we'll walk through it together. This is the next acceleration formula we're dealing with. So again, first step is read the question, write down the givens as the question tells them to. Golf ball is initially traveling at 25 meters per second. Okay, it doesn't give me a direction there, okay, but I do see a negative later in the question, so I'm just going to remind myself that this is positive. Okay, it hits a sand trap and slows down with an acceleration of negative 20 meters per second. Meters per second squared, sorry. Okay, find its displacement after 2 seconds. All right, so there's the information I have. I have VI, I have A and T, but I'm looking for D. All right, the only formula I have that has those 4 things in it is this one. Okay, it has A, it has T, 2 places. Right? It has VI and D. Now, the question's asking me to solve for D, so I don't have to manipulate. I just have to plug in my numbers. All right, so D will equal, okay, VI, which was 25, times our time, which was 2 seconds, plus 1/2 times the acceleration, which was negative 20, and it's crucial that the negative gets in there, right? Otherwise, you're going to find you're going to get an answer that's ridiculous because you were telling it was speeding up and not slowing down. Okay, and then we multiply that by the time squared. Right, so that's our numbers plugged in. All right, so we got 50. That's 25 times 2 plus 0.5 times negative 20 times 4. All right, so its displacement is 10 meters. Right? And since they didn't give me a direction on that, I'm just going to write positive. Okay. They gave me the acceleration to be negative, so I'm going to say the opposite of that is positive. Positive 10 meters. Okay. We're all right with that. So, manipulation of this one can be a little bit tricky. In fact, I had to go over it myself this morning. Because, okay, t is in two places in this equation. Does it kind of look like any equations you've dealt with in math? No? Like you have to factor it? Yeah. You don't have to solve for t if vi is not 0. Okay? If vi is 0, solving for t is easy. If vi is not 0, you have to factor the equation in order to solve for it. Since we can't guarantee that you've taken Math 20, where you learn to do that, which probably none of you have yet, okay, we can't ask you to do it yet. Yay! Okay, so you won't have to solve for t if vi is anything other than 0. Okay, so let's look at some manipulations of this equation here. Okay, so d equals vi times t plus 1/2 at squared. All right, what if I needed to solve for vi? Okay, I move what's not attached first. There's a lot of things not attached to vi. But
Divide by 80 squared.
I wouldn't divide, I would do the opposite of what I'm doing, which is
Subtract.
I would subtract. Yeah, okay? So I'm adding 1/2 at squared. I would subtract 1/2 at squared. So d minus 1/2 at squared equals vi times t. What do I do with the t?
Divide.
Divide. Okay, now here's a mistake people make. This does not cancel that. Okay, people do that automatically because they see a t on the top, t on the bottom. They cancel. No, they don't. Okay, this is a subtraction operation up top. If it was all multiplication, yes, you could cancel it. There's a subtraction operation in here. You can't. Okay, that's the formula solving for vi. Okay. What if I need to solve for a?
Divide by pi and t first.
No, I would do the opposite of what I'm doing with it right now. Vi times t plus 1/2 at squared. How do I move vi times t? I subtract, right. So d minus vi times t equals 1/2 at squared. I want a by itself. These are all being multiplied, so to move them, I divide. See why I don't like triangles? Good luck getting a triangle to do that for you. Okay? It will not. Okay. So that leaves us with A. Okay, there's the manipulation. Do I have to remember the rules of algebra? Yes. Is this going to require me to work out my algebra muscles? Yes. Okay? You've got to be able to manipulate equations in this course.
Do you ever have to solve for 1/2?
No, because 1/2 is 0.5. Right? So no, you never have to solve for that. It's a number we already know. Okay. What if I needed to solve for? What if I need to solve for t?
Has to be 0.
That's it. Which t, right? Okay. So if you have to solve for t, it will only be in a situation where vi is 0. Because what will that do to this t? Make it 0. Okay, so if vi is 0, vi times t is also 0. 0 plus 1/2 at squared is just
0.
no. 0 plus 1/2 at squared is just 1/2 at squared. Now I can solve for t. Okay, I just divide both sides by half of a, and then what?
Square root.
Okay, so if you're asked to solve for t, that'll be the situation in which you would do it. Okay, otherwise you got to use like the quadratic equation and do all this factoring crap.
Can you show
It's
us?
a nightmare. You know what? I could, but I don't want to. No, it won't help, because you'll never be asked to do it. Okay? All right. So, everybody okay with that one?
Yes.
So I want you guys to try these two. Okay, the first one's asking you to solve for displacement. The second one is also asking you to solve for displacement. Neither one's asking you to manipulate that equation left for you guys. Okay, but let's see if you can get them. Watch for little tricks like units, especially in question number 2, where it gives you kilometers per hour, meters per second squared, and minutes. Remember, all of the units have to match. So I would use meters per second and seconds in here. Okay, we got a skier moving down a uniform slope at 3 meters per second. So VI will be 3.0 meters per second down. Okay? If the acceleration down the hill is 4 meters per second squared, okay, down, okay, then find the skier's displacement after 5 seconds. Okay, and we're looking for the displacement. Okay, that's our question mark. So, D equals VI times T plus 1/2 AT squared. I don't have to manipulate it, I just plug in. So 3 times 5 seconds plus 1/2 times 4 times 5 squared. Okay, so when we're punching that all into the calculator, right, it should look like this. 3 times 5 plus 0.5 times 4 times 20. Times 25 squared. All right, so we're getting 65 meters, and I shouldn't say down, I should say 65 meters downhill, because that's more specific. Down and downhill are different. Down would imply straight down, okay? Downhill would imply at an angle. How many people have done number 2?
No, I have not. I don't think I'm right.
What do you need to do to the kilometers per hour? Change it to meters. Divide by 6.6. Okay. What do you need to do the minutes?
Divide by 3.6.
Multiply by 60. Yeah, because in 1 minute there are 60 seconds. It's pretty straightforward. Okay. Okay, so let's have a look at number 2 then. Right, so in this one here, okay, motorcycle's traveling at 100 kilometers per hour. So VI will be 100 divided by 3.6, like what, 27.7 or something like that?
2777.
Yeah, okay, so I'll just get that number in my calculator so I have it. 100 divided by 3.6, okay? 27.7 repeating. Okay, and then it applies the brakes. Now, the other trick in this question is, if it's applying the brakes, this is forward. The acceleration is backwards. So that 0.8 needs to be negative. Okay, and it does that for 1 minute. Not 6.0, 60 seconds. Okay, how far did the motorcycle travel? Yes.
Wouldn't the meters per second be bigger than the kilometers per hour?
No, aren't you going to go less meters in a second than you would go kilometers in an hour?
100,000 meters, 3,600 seconds.
Yeah, you got 100,000 meters in 3,600 seconds. Divide the 100,000 by 3,600.
Oh.
Okay, so we're looking for D here. Okay, so D equals VI times T plus 1/2 AT squared. So when I plug in my numbers here, that's going to be 27.7 repeating times 60 seconds plus 1/2 times negative 0.8 times 60 squared. Right? So when we're plugging all those numbers in, plus 0.5 times negative 0.8 times 60 squared. All right, so we get 226, but we only have 2 significant figures, so that'll be 2.3 times 10 to the 2 meters. And it doesn't give us a direction, so okay, we would just say positive.
I use significant digits in math as well?
It depends what your math teacher tells you. I don't know. In math, you're not always dealing with measured stuff. You're just dealing with numbers. Okay. Other Easton questions? Yes.
Could you also just convert it to kilometers?
You could, yeah, as long as you kept it at 2 significant digits. So it would be 0.23 times 10 to the minus 1 kilometers. Yeah. Yeah. That seems like a lot more work. But yes, you could do that if you wanted. Okay, copy this one down. Next formula to look at. So for this example, okay, we've got a speedboat that's slowing down at a rate of 5 meters per second squared. So I need to make that acceleration negative. Okay, and it comes to a stop. What's VF? 0. Okay, if the process takes 15 seconds, so that's a time, okay, find the displacement of the boat. All right, so I only have one formula that has these 4 things in it, and it's the counterpart to the one we've been using. Displacement equals VFT minus 1/2 AT squared. All right, remember that when we talked about these 2 formulas yesterday, we said they look at this graph, meters per second and seconds, and they both calculate the area under the line, but they do it differently. The one we were using before calculates this area here, VI times T, and then this area here, 1/2 AT squared. The other one calculates, the one we're working with now, calculates this whole box and then subtracts this area. Okay? The whole box is VF times T, then it subtracts the triangle. Either way, we get the area under the line from either one of them. Just one, we can do it using VF, and the other using VI. Okay? All right, so in this one here, I'm solving for D, so I don't have to manipulate. Okay, I'm just going to take 0, okay, because it comes to a stop, times T, which is 15 seconds, which really doesn't matter because it's 0, minus 1/2 times negative 5 times 15 squared. All right, everybody with me on that? All right, so I have to remember to keep the 0 in here, though. Okay, when we were doing the VF times T, or the VI times T, we just took it out. But now that I'm subtracting, it's got to be 0 minus a negative number. I'm going to go into the negatives here. Okay? I'm sorry, I'm going to go into the positives here, 0 minus. Okay, because I'm still moving forward. Even though I'm slowing down, I'm still moving in a forwards direction. So, okay, I'm going to have 0 minus 0.5 times negative 5 times 15 squared. All right, so we're looking at 562.5 meters. I only have 2 significant figures there, so it'll be 5.6 times 10 to the 2 meters. And they don't really give us a direction there, so we could say positive or forward. Okay? Manipulation of this formula is basically the same as the last one. Okay? If I want to solve for A, okay, what do I have to do to VFT? Subtract it. It's positive on this side. Okay? So I'm going to go D minus VF times T equals negative 1/2 AT squared. Okay? The negative stays there. All right. If I want to solve for A, now what do? I divide by negative 1/2 of T squared. Okay? That leaves A positive. Okay? Brings the negative 1/2 T squared over here, and I'm solving for A. The negatives, keeping track of the negatives is important, because if you don't, you're going to get the wrong vector on your answers, which is not good. All right. If I want to solve for VF, okay, then what do I do with the 1/2 AT squared? Add it to both sides. So D plus 1/2 AT squared, right, equals VF times T. Then I just divide both sides by T, okay, and I'm solving for VF. All right. If you have to solve for T, VF will be 0. Okay, so in that situation, we would have D equals 0 minus 1/2 AT squared, and we'd be solving for t. So effectively, we can just say this, negative 1/2 AT squared, divide both sides by negative 1/2 of A, and then square root. Again, there's a fair amount of manipulating here with these acceleration formulas. We just have to be ready to do it. All right. Try both of those. You can do number one. It's asking you to solve for t, but the plane is actually being stopped. So VF is 0. Okay, watch it up here, guys. So question number one, okay? We've got an arresting device that's stopping a plane. So we know VF equals 0 meters per second. Okay, it does that in 150 meters with an acceleration of negative 15 meters per second squared. Okay, that's severe, right? Like that is a harsh acceleration. That's more than gravity. Okay, so you'd get thrown into your safety harness really hard. Okay, like you almost get whiplash every time you stop on an aircraft carrier. Okay, which is why it's farcical that Tom Cruise could still be a pilot at his age flying F-18s. Did you look it up?
Yes.
He said he was only your age. Did you look it up on
He's not my age. He's way older than me. Thanks, though. I feel awful now. Okay. All right. So we're looking for. I don't have the benefit of billions of dollars of plastic surgery, so like that's.
You look like 40-something.
Don't try and charm me now.
What?
Okay, so we got this formula here that we're using. T equals VF times T minus 1/2 AT squared. But because VF is 0, I can eliminate this part of the equation as long as I keep the negative there. And now I'm solving for T. So I'll divide both sides by negative 1/2 of A. And then square root in order to get t. So t will equal, in this case, the square root of 150 divided by negative 1/2 times negative 15. It's important. Here's where it's super important to remember all the negatives. If I don't keep all the negatives, what will my calculator tell me when I try to do this?
Error.
It'll say error. Okay? Because you can't take the square root of a negative number. So if that ever happens, you forgot one of these two negatives. Okay? All right. So when we're solving for this, okay, we'll have the square root of 150 divided by, and then I have to bracket the bottom so it does it in the right order. Negative 0.5, see I almost did it. Negative 0.5 times negative 15. All right, so I'm getting that that's going to take 4.5 seconds. Okay, which is what they've got, 4.5 seconds. Nice. All right, try. How many people have done number 2? All right, I'm going to give you a few more minutes on number 2 then. Okay, let's get to it though. So on number 2, they give me the time, 6.2 seconds. Okay, they tell me that it accelerates to 160 kilometers per hour, which is 100 miles an hour, but I need it in meters per second. So 160 divided by 3.6 gives me 44.4 repeating meters per second. Okay, so now I've got that. Okay, and it traveled 220 meters. Okay, and they're all north. So I'm looking for the acceleration. So D equals VF times T minus 1/2 AT squared. So if I want to get A by itself, I'm first going to subtract VFT over to the other side. So D minus VFT equals negative 1/2 AT squared. I divide both sides by negative 1/2 of T squared. Okay, that'll leave me with A on this side. Okay, and now I can solve for A. So A will equal, sorry, not square root. A will equal 220 meters minus 44.4 times 6.2 seconds divided by negative 1/2 times 6.2 squared. Okay, so when we punch all that in, we're going to have 220 minus times 6.2, right, divided by negative 0.5 times 6.2 squared. All right, so I'm getting that this should take, the acceleration, sorry, would be 2.9 meters per second squared, north. On that one, only if we know for sure that it started from rest, and we don't know that. Okay, it's because they didn't explicitly say that, it's not safe for us to do it that way. But you're right, if they did say that, then that would be the quicker way. Easy question.
In that equation, is the 1 over 2, is that a negative 1 over 2, or is that minus?
Well, it's minus, but when I moved the VFT, I had to leave the minus there. That's why it kind of became negative, right?
So when it has like a sig sign in front of it, you can do it.
Yeah.
Keep them no matter what.
Yeah. Okay, last one. Copy this one down.
Bullet.
Okay.
Read my mind.
All right. Copy that one down. And we'll talk about it here in a second. So in this question, okay, we have a bullet accelerating the length of the barrel of a gun. Okay, that's guns when the bullet is struck by the hammer, right? The gunpowder explodes and the expanding gases accelerate the bullet out the barrel. Okay, the length of the barrel, the longer the barrel, the longer the acceleration. Okay, so we're getting a distance here, or a displacement of 0.750 meters, and the acceleration has a magnitude of 5.35 times 10 to the 5 meters per second squared. Is that a lot? Yes, I mean, when you figure that a bullet, when it leaves the barrel of a gun, is going faster than the speed of sound and has to get there in less than a meter, the acceleration is significant. Okay?
5 million?
It's a lot. It's not 5 million, no, it's 535,000. Okay? All right, so we're looking for, and we would also have to assume here, is the bullet moving at the beginning?
Yes. No.
No. Okay, bullets aren't moving when they're in the barrel, or sorry, before they get struck. Okay, so VI equals 0 meters per second. We're looking for the speed it exits the barrel at. So I have VI, I have A, and I have D, and I'm looking for VF. The only formula we have that has that is this one. VF squared equals VI squared plus 2AD. Okay, so this is our last formula for acceleration. Now, for this one, I really don't have to do any manipulating except that I don't want to find VF squared, I want to find just VF. So I have to go that VF equals the square root of VI squared plus 2AD. Okay. Now VI in this case is 0, so that's kind of moot. Okay. What we'll have here is VF equals the square root of 2 times 5.35 times 10 to the 5, okay, times the distance, which was 0.750 meters. All right. So square root of 2 times, and then in brackets 5.35. 0.7. Okay, so when it leaves the barrel of the gun, it is moving at 895 meters per second. To give you an idea, that's nearly 3 times the speed of sound.
That's why you can't see it, right?
Now you can see it, but you can't hear it. So that means that if someone shoots at you with a rifle, you'll be dead before the sound gets to you.
Unless you see the flash.
Well, you still won't hear it. You'll just see the flash. Okay? But yeah, a bullet does travel faster than the speed of sound. Okay? And so as a result, you don't hear it before it strikes you. Okay? Scary thought. If it's from a rifle, okay? If it's from a pistol, they're slower.
But then happened to the VF squared?
What happened to this?
No, where's the VF squared happening to the squared part?
I square rooted.
For the
When it's squared,
there is
it's
The VI squared.
VI was 0.
Oh, like 0 squared.
Okay, listen up here, guys. So tomorrow, we will be doing a lab on acceleration. Okay? We will not have a quiz tomorrow, but I'm going to bump it to Friday. Okay? Pardon me? Yeah, we're using the cart, so you need that SparkView app on your phone for a while.